All right, so with this week, we're covering systems of equations, and a lot of people get hung up on Gaussian elimination, and especially they get hung up on equations that have 3 equations, or I've had some people get hung up on non-square systems. So I'm going to go over Gaussian elimination and kind of connect it to matrices, and which is going to be next week. And then I'm going to do a couple examples to kind of show you the process. So Gaussian elimination is the name of an algorithm that we use to solve linear equations. It's the name of the process that is used. It's not like a shortcut formula or anything like that. It's an actual step it's you follow these steps, then you look at what you have, then you do these steps kind of thing. But it's really hard to kind of put into like a step-by-step because it's more critical thinking and problem solving than something specific that you can code really easily. So when we solve with Gaussian elimination, we're using a combination of both the substitution method of solving, and we use it in this case for back substitution. And then we also use a combination of elimination. So what we basically do is you start doing the elimination process until you get to a certain point, and then you do substitution from that point. Most of the time we don't actually do this by hand. We use matrices to do this, and we often use technology to do this. Matrices are specifically everything about week 3. I'm going to sort of introduce you to both, kind of show you side by side what they look like. And computers are really easy to work with when it comes to matrices. It's really nice to program with them because you're basically just creating arrays. So that's sort of when you're running a program that has to solve something, they usually do it in that form versus the form that we're doing where we're solving by hand. But doing it by hand can help you understand what it is that the computer is doing and what a matrix actually means, so you can see what's actually going on, because if you look at just a matrix, it's just a series of numbers, and so it's kind of harder to put it into context. So just to give you some background on matrices, so it's matrix and then the plural is CES. This actually comes from, I forget if it's Greek or Latin, but they have weird endings where the X turns into a CES. And a matrix is basically writing an equation without variables. You put all the variables on one side on the left and then the constant on the right. And then when you write it as a matrix, you only write down the numbers and you leave off the variables. And so each column of the matrix represents a specific variable. So the first column is X, the second column is Y, and then the third column here is the constant that it's equal to, and then each row represents a separate equation. So it saves some work as far as what you're writing because you're only writing numbers. It's really good for computers because there's less information that you're storing. So if you have a lot of data, which you often use matrices with, you don't have to worry about storing the variables, and it takes less space on the actual computer, less space in memory to solve. And so that's one of the reasons why they're used a lot with programming. It's like a shortcut kind of thing, but it means the same. You're doing the same steps that you would by hand. So when we do Gaussian elimination, we have a specific goal of or format of what we want our equation to look like, and that is called a row echelon form. And it's basically sort of a stair step where your top equation has every variable, then the next equation has one less variable, and then you keep subtracting or removing a variable so that your equations form a stair step, but it's like an upside down stair step because you have it's top down versus the other way around. If we were to put this in a matrix, what's important here is that for each row, the first term that you have has a coefficient of 1. So in a matrix, you see that you end up with the 1s in a diagonal. And then anything to the right of that can be a number. It doesn't matter what the number is. So your goal is you're trying to get the leading term and the leading coefficient to be 1. You don't care what anything else is, and it forms this stair step, and in a matrix you just put zeros for those blank things. And we set it up this way because then it's really easy to substitute. So if we have here this 3-variable, 3-equation system, when you put in this form, you know what z is, and then you can plug z in to the equation above it. It's really easy to solve for y. Then you know z and y, and you plug those into the top equation, and then it's really easy to solve for x. So plugging that in, that's called back substitution. So what we're going to do is a lot of manipulations to put our equations in this form, and then it makes the substitution part easier. So there are 3 things that we're allowed to do basically when we're solving systems, and these are called row operations because when you look at it as a matrix, you're basically doing things with rows of a matrix. So we're allowed to interchange equations, which is equivalent to basically flip-flopping rows or changing the order of the equation, how it's written, which one's on top. We are allowed to multiply an equation by a number, a non-zero constant. Multiplying by 0 doesn't mean anything. It just makes it 0. That's a rule you already know from solving, is that you can multiply both sides of an equation by a number. So that's nothing new. And then we can add an equation to another equation, which is what the elimination method does. But we can also replace equations with that result. And that's going to be the trick to put it in a certain form, is as we create these new equations from combinations of other equations, we can put the equations with fewer variables and replace them and kind of whittle down our system. And so these are the same things that we do with matrices. So I'm going to start with a 2-variable system, 2 equations, because that's easy to start with. So our goal is that we need to have the first equation to have 1 in front of the x, and the second equation needs to have only y in it because we need to remove a variable. So our goal is to have a system where x plus something equals something, and then y equals something. So we're trying to put this in a specific form, which is the row echelon form. So the way that you work to try to put these in this form is you sort of work from the bottom equation up. So we want to get rid of x in the bottom equation or the second equation. That's our goal. We need to get rid of that. So we're going to do this by elimination. If you're looking at our system here, if I multiply that second equation by 2, then I'm going to have negative 2x and 2x for the 2 equations, and we'll cancel out when I add them. So that's what we're going to do for our first step, is we're going to eliminate x because we want to get just y in that second equation. So when you're solving systems by hand, it's really important to be very systematic about how you're showing your work so it's easy for you to check. So I like to write down what I'm doing. So we're going to multiply the second equation by 2. So I'll write down 2 times equation 2. And then I am basically adding that to equation 1. So equation 1 is staying the same. We have negative 2x plus 3y equals 10. And then I multiply that second equation by 2, and that gives me 2x plus 2y equals 0. So we're going to do elimination. So we're going to add those together. Negative 2x plus 2x is 0. 3y plus 2y is 5y. And we get 5y equals 10. And then from here we would go and we would solve for y. Our goal is to get y by itself. We don't want 5y equals 10. We want to have just 5y. So when you're solving by elimination, that's what you do. That's your step. But Gaussian elimination doesn't kind of do that all in one step. So what Gaussian elimination does is it will do that, and then it will replace equation 2 with that result. I'm going to indicate that by doing an arrow, and that's going to be the new equation 2. So when you do this, we rewrite equation 1, and then we rewrite what we got with equation 2, and we now have a new system. So Gaussian elimination is taking everything and doing one step at a time and then writing your result. So you're not doing more than one thing. We're trying to keep it very clear what we're doing. And if you're writing this as a matrix, and I'm going to do the matrix in green, you're basically just taking the coefficients. You put a 0 if that variable is not present, and you write your result. So we generally will do a multiplication and an addition at the same time, but then we don't do like a division at the same time. So we only combine a multiplication with an addition step. We don't do more than that. So I'm going to just write this, that this is the matrix form. So now we eliminated x. For that second equation, the bottom equation, we need to have just y. So we're going to divide both sides by y. And when we're working with Gaussian elimination or with matrices, we usually indicate this by multiplication instead of division. So dividing by 5 is the same as multiplying by 1 over 5. So we indicate this by doing 1/5 times equation 2. And then I'm not going to add it to anything. I'm just going to replace equation 2 with that result. And so generally that multiplication step is easy enough to do in your head, so then you rewrite it. And we're not touching the first equation at all here. And we end up with y equals 2. And so if you were doing this with a matrix, again, you're just looking at coefficients. So you're just literally, with the matrix, what's really nice is that you're just multiplying the numbers. You just multiply every number in that second row by 1/5, and that gets you the new row, essentially. So now we have our bottom row in the correct form. Now we need to start working on the row above it. So we have x plus something. We need to get that coefficient in front of the x to be gone. So we have a -2. We need to get rid of -2, and we do that by dividing, or basically by multiplying both sides by a -1/2. So we indicate this by a -1/2 times equation 1, and then I'm going to replace equation 1 with that new result. So I'm just going to indicate that that is going to be stored as equation 1. That's sort of similar to how you might indicate things in programming. If any of you guys are going into computer programming, you're basically making a new, you're storing it into a different location or in the same location. So I have my system, and now notice I'm including that curly brace each time that I write my system. If you don't include the curly brace, you're not indicating that you have a system, you just have random equations. It's the curly brace there that indicates this is a system, these equations are being taken together. So that's really important. When you're told to write a system, you need to use those symbols, because otherwise you don't have a system, you just have random equations. So I've got my curly brace, and then I'm going to multiply that first row by -1/2. So that gives me x, because -1/2 times -2 is 1. And I have a -1/2 times 3. So that's going to be -3 halves y. And then -1/2 times 10 is -5. And then the bottom equation is staying the same. So if you're writing this as a matrix, We would then have 1, -3/2, -5, 0, 1, and 2. And the key with the matrix, when you're writing matrices, you have to have a bracket surrounding it. If you don't have those brackets, you're not indicating a matrix. So that's another thing where symbols are really important here because they're telling you what you're looking at. So now we're in row echelon form because now I have this little upside down stair step with my coefficients for those first terms being 1. So now we're going to do the back substitution step. So I'm going to go to another slide and I'm going to rewrite this equation so that we have that in front of us. So we have a curly brace, we had x minus 3/2 y equals -5, and y is equal to 2. So this is our row echelon form. So once you're in a row echelon form, that's where you do back substitution. So I'm going to just do this in a different color to indicate that. So the back substitution basically says that we know what y is now, so we're going to plug it back in to the first equation. So we have x minus 3/2 times y, which is 2, equals -5. And then we solve for x. So 3/2 times 2, that gives you 3, so that's x minus 3 equals -5. Then I'm going to add 3 to both sides. X equals -2. So once you get your next variable, you're done. You've solved the system. And so your answer is -2, 2, because we have to have the x first and then the y first. And you may be thinking, well, this seemed like a little bit extra work than just doing elimination on a system like this. And you're right, it is extra work to do Gaussian elimination. There's a couple extra steps here. We had to, instead of just solving directly for y by dividing both sides by 5, we had to kind of rewrite it differently. And then instead of just then plugging that directly in and solving for x, we had to rewrite the second equation. So it does take more steps when you're solving this way for just a 2-equation system. But the advantage is that this is easier to solve because it's just a little more formulaic in a way. So it's easier for you to program something like this because you have certain things that you're looking for and it's a little more formulaic. The advantage to this comes across when we have something with 3 variables. That's where you really find that Gaussian elimination is nice because it helps you keep it makes something that can be very, very complicated turn into something that's a little more step by step. You know what you need to do and you do the same thing every time. And it kind of helps you keep organized better. So for a 2-equation, 2-variable system, not really helpful. I mean, it doesn't really help in any way, but for 3 variables, it's really helpful. So I'm going to actually do one of those right now. So let's say we have a 3-variable system. So we've got 3x plus 4y minus z equals 17. 5x minus y plus 2z equals -2. And then 2x minus 3y plus 7z equals -21. So we've got 3 variables, 3 equations. When you have 3 variables, 3 equations, that is something that you can solve. There's going to be a solution. It's if you have, say, one variable and two equations, that's something that we call overdetermined. You have too many equations, and if you have maybe three variables but two equations, so you have more variables than equations, that generally means that there are infinite solutions because you don't have enough information to determine what the answers are. So in order to solve something with three equations, you need to have three variables. So our goal here is we need to put this into a system where you have x plus something y plus something z equals something. Then you want to have y plus something z equals something, and then z equals something. So we have to do this sort of upside down staircase, and it's going to be a lot of steps. It's a very lengthy process doing it by hand, very prone to errors, unfortunately. So it's always good to have technology to double check your answer, just to check yourself. You can use Wolfram Alpha is actually the website that I usually use. It's really nice for checking your answers. You can type in all three equations or write solve, and it'll do it for you. It'll give you the answers, not the steps, but you can use that to double check because it's really easy to make mistakes with this many equations. So we have to be very systematic here. And so in general, what you do is you focus on the x's first, because we need to get rid of x in both the second equation and the third equation. So that's what we're going to be focusing on. We're going to be trying to get rid of these, and we're going to be using elimination to do it in combination with the first equation. So I'm going to work with the first and the second equation in order to eliminate x. So just write this down. Eliminate x using equation 1 and equation 2. So the easiest thing is to multiply the first equation by -5, the second equation by -3, so that we can do this elimination. So however you show your work here is fine. Sometimes what people will do, let's see, so let's do first equation by, let's say, -5. And then if you want, you can just do like E1 for equation 1. And then we need to have opposite signs, so I really only need to multiply the second one by 3. Oops, and then we can just label that E2 if you want some sort of shorthand there. So then I'm actually going to do that multiplication. So I'm going to show the result on the right. So I've got -15x minus 20y plus 5z equals, and then I don't know that one in my head, -85. So if you see any math errors while I'm doing this, please let me know, because it's very easy to make an error in your arithmetic with your multiplication, you're adding something like that. 3 times 5 is 15x. We get minus 3y. That's plus 6z equals -6. So on that, now I'm going to add them to eliminate x. We end up with -23y plus 11z equals -91. So it looks like we're going to get some kind of nasty numbers here. And this is going to be stored as, this is going to now be equation 2. Because in equation 2, we want to get rid of that x. So this result is going to now be equation 2. So I'm going to just rewrite what we have. 3x plus 4y minus z equals 17. -23y plus 11z equals -91. and then 2x minus 3y plus 7z equals negative 21. Now you may possibly be thinking here, well, what if that first equation with 3x, we got rid of the 3 to put it in the right form there, and then we started doing this elimination? And you can do that. I tend to not do that right away because often it gets fractions. So if we divided the first equation by 3, I'm now going to have a 4/3 y. I'm going to have a negative 1/3 z. I'm going to have a 17/3. And then your whole system is going to end up with fractions all over the place. And it's just, then it's even more likely that you're going to make a mistake, because then you're trying to add fractions with things that are not fractions. And so I usually put all of those dividing steps, I save those for the end, for the last thing, just so I avoid creating fractions that can complicate things. So I've eliminated x in the first equation. Now I need to eliminate x I eliminated x in the second equation. Now I need to do it in the third equation, and I'm going to do that using equation 1 and equation 3. So we're going to eliminate x using equation 1 and equation 3. So for the first equation, I can multiply that by 2. The third equation, I can multiply that by negative 3. So I'm going to be doing some flip-flopping here. I want to do 2 times equation 1, negative 3 times equation 3. So that's 2 times equation 1. That's going to be 6x plus 8y minus 2z equals 34. It's a lot easier when you have this all on one sheet of paper and you're not doing it on slides. You don't have to flip-flop back and forth. And then negative 3 by the third equation. So that's going to be a negative 6 and a positive 9. Negative 21. And then negative 21 times negative 3. That's going to give me a positive 63. So always double check you've done your math correctly. The 6x and negative 6x cancel. 8y plus 9y is 17y. We have a negative 2z minus 21z, so that's minus 23z. And then 34 plus 63 gives us 97. And now this is going to be our new equation 3. So I'm going to rewrite. We had 3x plus 4y minus z equals 17. Our second equation is negative 23y plus 11z equals negative 91. And now we just got 17y minus 23z equals 97. So I need to make sure I gotta add some more slides. I didn't add enough blank slides on my thing here. Okay, so let me add a few extra blank slides to make sure I've got enough. All right. So now we've gotten rid of all of the x. I'm going to go back here. Now our next step is we want to get rid of the y in the third equation. So we want to eliminate this right here. And it doesn't matter which equation you use, or it does matter actually, because if you do it with the first equation, then you're going to end up with x again. So to eliminate y here, you have to use equations 2 and 3, because those are the only ones that have only those variables. If you tried it with equation 1, then x would end up back in your thing again. So our numbers are going to be gross here because we've got negative 23 and 17. But as long as you have a calculator, you can do this. So we are going to have to multiply equation 2 by 17, and then equation 3 by 23, essentially. So I'm going to write this down. So we were going to eliminate y using equation 2 and equation 3. So equation 2, we're multiplying by 17, and then equation 3 is getting multiplied by 23. So the signs are already going to be opposite. So negative 23 times 17. This is also make sure you type things into your calculator correctly because it's very easy to mess up. We got negative 391y and 11 times 17. I have plus 187z, and then negative 91 times 17, negative 1,547. Now I've got 23 times E3, so I'm going to take that third equation, multiply it by 23. So again, the 23 times 17 is 391, so we get 391y. 23 times a negative 23, minus 529z, and then 23 times 97, 2,231. Large numbers here, calculator definitely requires. So now I'm going to eliminate y. So the y's cancel, and then I have 187 minus 529. I get negative 342z. And then we get negative 1547 plus 2231, 684. So what we have so far, we've got 3x plus 4y minus z equals 17. Our second equation hasn't changed. We have negative 23y plus 11z equals negative 91. And this third answer, that needs to be replaced with equation 3, because that's where we want to have just the z. So then I have negative 342z equals 684. So we're not in row echelon form yet because we have coefficients in front of each of these, the x, the y, and the z. So we need to divide both sides of z, or the last equation, by negative 342. So if you want to be lazy about that, you can do this and just say equation 3 divided by negative 342. So if you want to be sort of lazy, that's fine, as long as you're writing down what you're doing so you can double check your work. And then I need to make sure that I still have my system. So the first two equations are not changing. You're seeing you're doing a lot of rewriting the same thing. And then I'm going to have z equals, and then 684 divided by negative 342. Z is negative 2. So that's good. We get a whole number. So we've got our last row now in the form that we want. The second row is not in the right form. We need to divide that by negative 23 so that we have just y in front of there. So we're basically going to take the equation 2, divide that by negative 23 so that we have just y. And really, if you want to combine your work, we can also divide equation 1 by 3. So generally with Gaussian elimination, you would do each of these things separately, but I'm not testing whether you guys are doing every step one step at a time. It's fine if you try to save some work, because we could have done all 3 of these divisions in the same step, basically. So I showed you step by step in that first example, but when you have a long example like this with 3 variables, 3 equations, you're trying to save paper, it's okay to combine steps. So we can do both of those divisions at the same time. So if I'm going to divide the first equation by 3, it leaves me with x plus 4/3 y minus 1/3 z equals 17/3. Then we divide our second equation by -23. We have y, and then 11/23z, and then -91. That does not divide. Does that reduce? No. So that would be then a positive 91/23. And then we have z equals -2. So the Gaussian elimination makes your stuff look really gross because we ended up with fractions here. But now is the back substitution step. So we got through all of the hard work. Now we actually want to plug in z equals -2 into the equation. Now we do have a lot of fractions here, so I recommend either you have a calculator that does fractions or you find an online calculator that can do fractions. The Desmos scientific calculator does fractions. It'll make your life so much easier so that you don't have to mess with getting things wrong and all of that. So I'm going to take the second equation because we need to plug that into equation 2. So we have y minus 11/23 times -2 equals 91/23. Now the nice thing here is we're going to get a common denominator, so it's not too bad to do it by hand if you want. So this is going to be y plus 22/23 equals 91/23. And we're going to subtract the 22/23 from both sides. 91 minus 22 is 69. And when I divide that, so we get 69/23, and that actually reduces, that divides evenly, and we end up with y equals 3. So now we have x, or now we have z. Now we just found y. So now we need to plug them in to find x. And I think I can even squeeze this into the same. If I just kind of squeeze it out here so I don't have to use another slide. I've got x plus 4/3 times y, which we just found was 3, minus 1/3 times z, so that's -2, equals 17/3. So x plus 4 plus 2/3 equals 17/3. I'm actually going to subtract my 2/3 first because that's going to give me a whole number. 17/3 minus 2/3. That is 15/3. And that is 15 divided by 3 is 5. So I really have x plus 4 equals 5. So then you can subtract 4 from both sides. Get x is equal to 1. Now that we found out x, now we have our answers. We have to put in alphabetical order. So we've got x first, which is 1, y next, which is 3, and then z, which is -2. So very long process, but the nice thing is that the steps are roughly the same every time when you try to follow this. You're always going to first try to eliminate x in those bottom two equations, then you're going to eliminate y in the last equation, and you're going to divide all of your equations by those coefficients, and then you plug things back in. Do you guys have any questions on this example?
Have any? I'm not a fan of it, but I don't.
You'll like matrices because it's a lot. I mean, it's almost the same amount of work, but it's easier to work with, and it just seems easier. So, and then with matrices, you're actually going to get to do. Well, I'll show you some technology that you can use for that as well. But yeah, I don't like doing these either. I prefer to not ever assign problems like this because it just takes forever. It takes a long time. So, but it is very procedural once you figure out what you need to do. Okay, so I put an extra. There we go. So now I'm going to show you guys the non-square system. And so non-square just means, we call it non-square because if you put it in matrix form, so we'd have 1, -3, 2, 18, 5, -13, 12, and 80. It forms a rectangle versus a square. So when it's in a matrix, it's a square system. If it literally just forms a square, those always have I shouldn't say always have. There are situations where you could have no solution or infinite solutions, but generally we'll have one solution. Non-square systems always have multiple solutions because you don't have enough information to get all three variables. So not enough information, you're guaranteed to have multiple solutions. And the key here is how you give those answers. But you go through the same sort of thing with the Gaussian elimination, where you are eliminating variables as much as you can. So we still want to put it in row echelon form. And our first equation is actually already in that form because we've got no coefficient in front of the x, so that's going to be really nice. So we want to eliminate x in that second equation. So we're going to multiply the first equation by -5. And then add that to equation 2. So it gives us a -5, x plus 15, y minus 10, z equals, this is where my calculator comes out, 90, -90, can't forget my negative sign, then 5x minus 13y plus 12z equals 90. 80. I am reading off the wrong number. Good thing I wrote the correct number. Okay, so our x's eliminate. 15 minus 3, 2y, -10 plus 12, that is 2z, -90 equal or plus 80 is -10. So if you're looking at our system so far, got x minus 3y plus 2z equals 18. Oops. And then we have 2y plus 2z equals -10. So to put it in row echelon form, we need to divide that second equation by 2. So that way we have just y there. So we're going to divide this by 2. So I'm going to rewrite this. We have x minus 3y plus 2z equals 18. And then we had 2y, so we divide that by 2. And we have the 2z, divide that by 2, so that's going to be plus z. And then we have negative 10 divided by 2, and that is negative 5. So at this point, we can't really go any further because we don't have a third equation for z. So this is as far as you can basically go. So we are in our Gaussian elimination, our row echelon form. So from here, we need to figure out what we're going to label for x, for y, for z. We have infinite solutions, and we don't have an equation that tells us what z is. So basically, what you do from this point is that you just say we are going to let z equals a variable, and we're going to call that variable a. So you could call the variable b if you want, c, whatever, but z can be anything because we don't have an equation here that tells us what z is. So z can be anything. We don't have that third row. So then you're going to replace that into your equation here for y and solve for y. So we end up with y plus a equals negative 5. We subtract a from both sides, and we get that y is equal to negative 5 minus a. Then you take that answer, and then you're going to replace that in the first equation. So that's going to go here, and z, our variable a, is also going to go in there. So we're still doing back substitution. We just now have another variable we're working with. And so we end up with x minus 3 times y, which is negative 5 minus a, plus 2 times a equals 18. And then you're going to solve this for x to get that expression here. We get x plus 15 plus 3a plus 2a plus 18. I subtract the 15 from both sides. Add the 3a and the 2a to get 5a. Minus 15 is 3. Subtract my 5a. I get x equals 3 minus 5a. So we write our solution using these variables for a. So our ordered pairs are 3 minus 5a, and we have negative 5 minus a, and then we have a. Now you may be wondering, well, why didn't you just leave it as z and do the same sort of thing, and you just don't know what z is? And that basically depends on the book, essentially, because some textbooks do that. Some textbooks will just leave it as z, and they just know that, okay, we don't know what z is. I can plug in any number for z, and everything is in terms of z, because that's the one thing I don't know. Our textbook does it with a, where they just create a new variable for a. So that's what I'm showing you here, but just know that it's equally valid to leave it with z. It just really depends on the convention and the textbook and that sort of thing. But basically, for a non-square system, we don't have enough information to figure out z. So you get infinite solutions, multiple solutions. I can make a 0 and get one solution. I can get a to be negative 5 and get another solution. You just pick a number for a, and that will give you a solution to this system. It's just not the only solution to the system. Do you guys have any questions there?
Really?
Okay. So that was the last of my examples and what I wanted to make sure that I went over with you guys. I'm going to make sure to I'll make sure that the PowerPoint's available, recording is available, so that way you can review it.